Start recording. All right, so this first question gives a conjugated diene and an alkyne. In class on Monday, we said that you can get a Diels-Alder reaction with an alkyne as the dienophile, especially when there are electron withdrawing groups attached, which we have here. So in order to figure out what the product is, we need to draw the mechanism. So we line up our dienophile with our diene. I mean, I don't know of a way of just looking at it and knowing what the product is. I think it's safest to draw the mechanism. And there are methyl esters. So to draw the mechanism, we move the 3 pi bonds. One of the pi bonds goes between these 2 carbons and makes a sigma bond. Another pi bond moves between those 2 carbons and makes another pi bond. And the 3rd pi bond moves in between those 2 carbons. If you find the visual aid of the dotted line helpful, you may add it, but it is not required, if that makes it easier for you to see what's going on. ChemDraw is complaining about both those carbons. It thinks they have 5 bonds. And so for every Diels-Alder, you will always get a cyclohexene, always. There's our cyclohexene. And you just copy down all the groups. There's a methyl group on that carbon. These 2 carbons are still CH2s. This triple bond becomes a double bond. And those 2 are the bonds to the methyl ester groups. We did an example very much like this in class. And if it will help to color code it, let's color the dienophile red. And the atoms in the dienophile are right there. So there you go. There's the answer. It's a Diels-Alder reaction. You'll notice I did not make any wedge or dot bonds. I stressed this in class 2. With alkyne dienophiles, these 2 carbons over here become alkene carbons, and they are flat. They are planar. So like I said, we need to disabuse ourselves of this notion that wedges equals points. It's not always the case. And that's basically it. So it's just a simple Diels-Alder reaction. How would you recognize it as a Diels-Alder reaction? I guess because you're given a conjugated diene. That limits it to only a few reactions. And then you look at what the diene's reacting with, and we recognize a dienophile. Alkynes can be dienophiles, especially, as I said, with electron withdrawing groups attached. So that's how you recognize it as a Diels-Alder reaction. Looks like we've got more chapter 14 questions over here. All three of these have conjugated dienes in them. This one asks, what would we need to react this diene with in order to get this aromatic compound? And this isn't something I stressed very much in either chapter 16 or chapter 14. It may be a little easier to recognize if we turn the top molecule so that it looks like this. And then you can see that this part of the molecule, which I'll color in blue, becomes this part of the molecule. And we've again undergone a Diels-Alder reaction. The two new bonds are this bond over here and this bond over there. Those are the two new sigma bonds. So somehow we have to get a dienophile that will add a benzene ring on in a Diels-Alder reaction. And the only dienophile that will do that is something we talked about in chapter 16, and I expect you still to remember. It's benzyne. Benzyne is a truly wonderful Diels-Alder dienophile. We didn't give an example with benzyne, but when you look at the structure of the product, you can see that these two carbons over here, where there is effectively a double bond, must have had one more pi bond in the starting material. So those two carbons are the alkyne carbons in benzyne. And like I said, we didn't do an example with benzyne. The way you would have to do it is you'd have to generate benzyne, which we talked about how to do in chapter 16, generally by taking a halobenzene and treating it with a strong base. There's other ways of generating benzyne as well that we didn't talk about. But we talked about how to do that in chapter 16. And yes, I expect you still to remember that. It's good practice for the final. So when you react this diene with benzyne, you get this Diels-Alder adduct. And I've color-coded everything as best as I can. So that's a good way of adding an aromatic ring on in a Diels-Alder reaction. Next, we have this one. Oops, that's not good. In which, as you can see, always with this type of problem, look at what has changed. And what's changed is this double bond has become a single bond with bromines attached to each of those carbons. That's the change in the molecule. And we know how to get two bromines attached to two formerly alkene carbons. We learned that in chapter 8. But not only that, we can see that the two bromines are right next to each other. So this is going to be an electrophilic addition, and this is the 1,2 product. We know that because the two bromines are right next to each other on adjacent carbons. And so we must have added bromine, but we did so under kinetic conditions. We did so in such a way as to get the 1,2 product to be the major product. And that's kinetic conditions. So that means that we added the bromine at low temperature. And just saying Br2 in low temperature is more than adequate. You could say Br2 in cold if you wanted to.
I have a question.
Sure,
So low temp is not the same as just putting heat.
low temp is the opposite of heat.
Okay.
Remember when we discussed electrophilic additions of conjugated dienes, we said that at low temperature, which generally means below room temperature, causes you to get the 1,2 product favored as the major product. And high temperature, meaning in general something above room temperature, will get you the 1,4 product favored as the product. So low temp means you're removing heat from it. Is that what you meant?
Yes, and if we did it over with the 1,4 product, would you please show what would it look like? Like with the bromines just attached to the fourth carbon?
Actually, it's the next problem.
Okay, okay.
In this case, the change that's made in the molecule is this diene has had the double bond shift in between carbons 2 and 3 and bromines going on the end carbons. So it looks like we've added Br2 again. It must have been Br2 because 2 Brs are added. But in this case, we're getting the 1,4 product. We know the first one's the 1,2 product because the 2 carbons that have the bromines on them are right next to each other. In this case, the 2 carbons that have the bromines on them are in a 1,4 relationship to each other. See how they're on carbons 1 and 4. And the double bond is migrated just like it always does. That's part of the mechanism. And so in this case, we must have added Br2, but at high temperature. No need to list a specific temperature. Low temperature and high temperature are fine. Warm is fine. Heat is fine. Anything that signifies a temperature above room temperature is
So
fine.
can we put like ice for low temp?
Sure.
Really?
I
Okay.
think our graders have enough imagination for that. You could put 0 degrees C if you really wanted to, which is the temperature of ice water. To make things easier on the graders, if this is on the exam, I think low temp and high temp are the best. But any close synonym should be fine. And if they mark something right, wrong, then you do a regrade request. That's what it's for. Good, so we discussed these reactions in chapter 14. If instead of these, we'd added HBr, or let's do HCl. Then we would get the 1,2 product. That looks like this. The 2 carbons that are involved are right next to each other. They're in a 1,2 relationship. On one of those carbons, the chlorine goes, and in the other, the hydrogen goes. This carbon is now a CH3. It had been a CH2. 2 of those hydrogens were there to begin with. The other one got added as a result of the reaction. And we went over that mechanism multiple times in class. Likewise, if we added HCl at high temperature, then we would get the 1,4 product. in which the double bond migrates in between carbons 2 and 3, and the hydrogen and the chlorine are in a 1,4 relationship to each other.
Problem in which we have to show like the curvy arrow mechanisms for these kind of reactions.
In general, the rule is you have to do everything it says. You don't have to do anything it doesn't say. The original question did not say to show the mechanism. It said write the reagents necessary.
Oh, gotcha. Okay. Sorry.
So much for those problems.
Do we need to know the mechanism for these kind of reactions?
Absolutely you do. We went over it in class.
Okay.
I'll even show you. The first step is exactly what we learned in chapter 6. The first step of the mechanism shows the electrons in the pi bond picking up H plus from HCl. You get an allylic carbocation, which looks like this. And then Cl minus attacks the carbocation, forms a new carbon-chlorine bond, and you get the product. We learned that mechanism in the first semester. The second product comes from the other resonance form of that carbocation. Which looks like this, has the plus charge, whoa, on the primary carbon. And then you show the chloride ion attacking that carbon and forming a bond to this carbon, which is it's the same compound. I'll show you. A and B are the same compound. It's just drawn from another angle. The way you know that is because you have cyclohexene with a methyl group and CH2Cl. Cyclohexene with a methyl group and CH2Cl. So they're the same compound. Everything shown needs to be shown. Anything not shown is okay not to show. Other questions? Now we get into some carbohydrate questions, which we started today. This question, we did one just like it in class today. D-talose is an aldohexose like D-glucose, except it differs in configuration from glucose at carbons 2 and 4. Draw D-talose in its open chain form, its chair form, and its Hayworth projection. We had class, the reason it says the way we did on YouTube, this exam comes from the COVID year when classes were online and everything was uploaded to YouTube. For the two cyclic forms, draw the beta anomer. We introduced all of these terms in class today. So in order to get this right, you need to know what glucose looks like. And glucose looks like this. We introduced this in class today. Your OH groups go right, left, right, right. Notice again how it draws the OH group on the left is HO. ChemDraw does that automatically. And so this is carbon 1, 2, 3, 4, 5, 6. And the question says, it differs in configuration from glucose at carbons 2 and 4. You don't have to draw glucose if it doesn't say to draw it. I'm just putting that there so that we have a visual aid. And so we're going to change the configuration at carbons 2 and 4. So the OH group will be on the left over here. And this OH group will also be on the left. And that's D-talose. It's like glucose, except it differs in configuration at carbons 2 and 4. And in order to draw the chair form, let's first look at glucose. Oh my, isn't that beautiful? They even bolded the bonds that are in front. So there's glucose.
Whenever we draw the structures, will we have to draw those bold stuff, like the wedge?
No,
We don't?
do
Okay.
it like we did in class today.
So we don't have to draw, we don't have to bold it. Okay, I was wondering if we needed to, because that kind of takes a bit of a time on the exam if we had to bold it, so.
I understand that. You do not have to bold it. You can do it like we did in class today.
Sounds good, thank you.
Just depress the point. How's that? That's how we did it in class.
That's even better, yep, thank you.
So there's glucose. It says to draw the beta anomer, and I believe I have here the alpha anomer. The beta anomer would have the OH group pointing up. Oops, what am I doing? That's better. So there's glucose. It says to draw the beta anomer at carbon 1. This is carbon 1, 2, 3, 4. Carbon 5 is the CH2OH. and carbon 6 is the CH2 in the CH2OH. So that's still glucose. I put it under D-glucose, so you'll see it's still glucose. In order to change that into talose, we need to change the configuration at carbons 2 and 4. So carbon 2 will have the OH axial, and carbon 4 will also have the OH axial. So this is glucose, this is talose. And in both cases, we have the beta anomer. Because the OH group is pointing up. And the way you know that the OH group is pointing up, it's hard to tell because the OH group is equatorial, and that's hard to see if it's up or down. You'll agree that the H on that carbon is definitely down. It's much easier to see when it's axial. So if the H is down, then the OH must be up. So that's how you would draw the chair form. We'll see if I can draw a good Haworth projection. A little too much angle over there. This is easier with a pencil or chalk. So there's my flat ring. We put the oxygen in this position. The way you know that is on the chair, the oxygen is in the upper right. So in the Haworth projection, the oxygen is also on the upper right. Whoops. So this is carbon 1, 2, 3, 4, 5, and that carbon is carbon 6. If it doesn't say to draw the numbers, you don't have to. I'm just doing it for teaching purposes so that people have clear visual aids about what's going on. And so on carbon 1, we have the OH group pointing up and the hydrogen pointing down. On carbon 2, the OH again points up. The hydrogen points down. You can tell easily that the OH is pointing up. So the H on the same carbon must be down. On carbon 3, the OH is up and the hydrogen is down. On carbon 4, the OH is up and the hydrogen is down. The CH2OH group on carbon 5 is always up if you have a D sugar. And I'm having trouble fitting that in. We'll do it like this. There's our hydrogen. So that's what the Haworth projection would look like. Again, the way to know if groups are up or down on a chair cyclohexane, or in fact, one of these sugars, the way to know is by looking at the axial group. Axial groups are very easy to tell as to whether they're up or down. And whichever the axial group is not, is what the equatorial group is. If the axial group is up, the equatorial group on the same carbon is down. If the axial group is down, the equatorial group on the same carbon is up. Always, there's no exceptions. So basically, what you would have needed to answer the question are these three things. And you don't even need the numbers, since it doesn't say to draw the numbers. I just did that to make it easier to see. So that would have gotten full credit. Now I'm going to copy this. So much for the first part of the question. Oh, I just lost my L-Talos. Or my D-Talos. I can get another one. Talos. It's not wrong to write CHO for an aldehyde group, and it would be accepted. It's just in my experience, these abbreviations like CHO, CO2H, CO2ET are confusing for students. So I've made it a point always to write them out. So here's our Talos. That's D-Talos. To get L-Talos, you would invert all 4 chiral carbons. So instead of left, 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 right, we have right, 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 left. And then in the other positions, we have hydrogens. That's L-Talos. It's the enantiomer of D-Talos. L-glucose would be left, right, left, left. L-glucose. So I just drew D-Talos to get L-Talos from it. The people taking this exam could just copy or use as a reference what they had drawn up here. So there's L-Talos and L-glucose. Then it says, draw the only 3-carbon sugar we discussed in class that's not chiral. That's simple. It's 1,3-dihydroxyacetone.
Didn't you say that there was another one? Like there were 2 other versions of the 3-carbon sugar?
No, there's 2 other 3-carbon sugars that are D and L-glyceraldehyde, but that's chiral.
Oh, I see.
The only one that's not chiral is 1,3-dihydroxyacetone.
Is that the glycerol molecule that's used for like lipids, fatty acid tails?
Very close. It's glycerol having been oxidized at carbon 2.
Oh, I see. So, okay, gotcha.
So for glycerol, that's an OH. So it's very closely related to glycerol.
But so this one's called triglyceride, right?
No, this one is called 1,3-dihydroxyacetone.
Never mind. Okay.
The structure of acetone you know from lab. It's what you use to clean your glassware. This is 1,3-dihydroxyacetone.
Got you.
So that was what was required for that question. Then it says to draw a disaccharide. That we're going to cover in class on Friday. But let me show you the basics of how to do it. It says to draw the disaccharide D-glucose, then a beta-1,6 linkage, then D-glucose. Oops, I don't want the straight chain form. I want the beta-pyranose form first. So there's D-glucose in the beta-pyranose form. You'll notice it says beta-1,6. That means we're going to connect two glucose molecules from carbon 1 of the first glucose to carbon 6 of the second glucose. And we're going to use a beta linkage. That means the OH group on the first glucose is beta. It's pointing up. And this is carbon 1, 2, 3, 4, 5, and 6 is the CH2. So that's our first glucose. And we're going to attach that to a second glucose. That glucose says at the hemiacetal carbon, of which there's only one, draw the alpha anomer. So I want the alpha pyranose form. And this is going to be our hemiacetal carbon. I expect you all still to remember what a hemiacetal is from chapter 19. There we defined a hemiacetal as something with a carbon that's bonded to OR and OH. So the hemiacetal carbon is the anomeric carbon. And there's going to be one hemiacetal left after we connect carbon 1 of this glucose to carbon 6 of this glucose.
Wait, but wouldn't that make that second glucose an alpha and not a beta? It's saying to draw disaccharide beta 1 to 6. That
Right.
second.
That's why I've put the OH beta on the first one.
Oh, but what about the second one? Shouldn't the second one also be beta? Well, I mean,
No, it says at the hemiacetal carbon, draw the alpha anomer. This is going to be our hemiacetal carbon.
so I think the wording, the beta 1 to 6, I thought that was referring to both, but that just refers to.
Nope, that's just referring to the first one.
Gotcha. Thank you.
And like I said, I haven't introduced this in class yet. We'll go over this on Friday. We'll do at least one example besides this one on Friday. So what we're going to do is connect the carbon 1 of the first glucose to the OH and carbon 6 of the second glucose. And I realize this is a lot easier than this moving things around on the computer is a lot easier than moving things around. You can't exactly do this with a pencil. But you basically want that oxygen I want it to be easier to see, so let's do this. Actually, let's do this. I know what we'll do.
On the exam, will we be counted off for putting numbers or when we draw the structures?
What do you think?
Your
Your best guess.
No, we will not.
That's a good guess.
So so then yes, we will be counted off.
No, you said no.
Oh, well, you said that was a good guess. So I was like,
Yes,
am I
it's a
wrong?
good guess. You guessed right.
Okay. Got you. Okay.
So this is beta. Whoa. I mean, I don't think you've ever seen anything like that happen on past exams. And as I've said many times, if you get something marked wrong that's right, that's what regrade requests are for. Good. So I think we now have everything. I've connected carbon 1 of the first glucose and carbon 6 of the second glucose with the oxygen. So essentially the molecule has lost H2O, or the two molecules have lost H2O and becoming one molecule. And we've got an alpha anomer at the second, at the second glucose's anomeric carbon, which is the only hemiacetal carbon in the entire molecule. This carbon here is no longer a hemiacetal. Now it's a full acetal because you have two OR groups attached. And so something like that would have gotten full credit. And like I said, we're introducing this in class on Friday, and we'll do at least one more example. And now, because I don't trust myself, really, what I'm saying is I don't trust past me. I don't know which I trust more, past me or present me. Where did that document go? Why did it not? Oh, I need the answer key. Also, since you guys asked before, you see on the answer key, it just has low temperature and high temperature. That is the same thing. I just drew a different bond angle going to the CH2 group. I should also mention, since I know students are extremely sensitive to every little difference, no. In class, I just wrote CH2OH like that. You may do that if you like, or you can write out the CH2 group like that with a line angle drawn. Both are equally acceptable. Not only will we not take off points, we won't even notice. It's the same thing. And I want you guys, after 2 semesters of organic chemistry, to have developed that kind of confidence. Of course, it's the same thing. One's a line angle drawn, the other is just writing CH2. There's no difference. Good, so there's your disaccharide. Next, oh, any other questions on the disaccharide? All right. Here where it says OWL, we would have active. OWL was what we had in those years for online homework. So what this is asking you to do is provide the reagents that will cause each of these steps to happen. In the first step, we're going from cyclopentanol to cyclopentanone. That's an oxidation reaction. The way I know that is we're going from 1 bond to oxygen to 2 bonds to oxygen. We're increasing the number of bonds to an electronegative element. That falls under the definition of oxidation. So we need an oxidizing agent. The one that ought to come most readily to mind is Dess-Martin periodinane. And that uses dichloromethane solvent. The second one has the ketone going to this tertiary alcohol. And you can see that what's changed is we've added this isopropyl group. So how are we going to add an isopropyl group to a ketone so as to make a tertiary alcohol? The best way to do that is with a Grignard reagent. And so step one would involve isopropyl magnesium bromide or magnesium chloride or magnesium iodide. And then for step two, this would require an aqueous acid workup. You can write it just like that.
Do we have to put ET2O?
That is probably a good idea. You can also use THF.
Or the answer key said 1, comma, and then ET2O. So,
Yes,
but if we don't have to,
I know
if
that
we don't
you're
have to,
following along with the answer key.
I mean, if we don't have to put it, then it's not a big deal. But
Well, let me just see what the answer key has. I consider them identical answers.
sounds good.
Probably safest to write workup since you mean you're not doing anything else by way of a reaction. You're just protonating O minus because you get O minus at first from a Grignard, and you need to protonate that. So that's a workup step. That means we're only doing acid-base reactions. I will change the answer key to match this. And any ether solvent is fine. THF is also fine. The next step shows going from a carbon-carbon single bond to a carbon-carbon double bond. And we've lost an H and an OH. That means we've undergone a dehydration reaction. Now I'm cheating looking at the answer key. So we need a dehydrating agent. Probably one of the best ones we've learned about is POCl3. Phosphorus oxychloride is a very good dehydrating agent. Thionyl chloride would also work, SOCl2. Acetic anhydride might work. Again, since I know there are people following along on the answer key, H2SO4 is fine. Concentrated sulfuric acid is fine. Then we go from the double bond to a single bond again, and we add a Cl and an OH. We add HOCl across the double bond. That's a chapter 8 reaction. That requires chlorine and water. We're making a chlorohydrin. So that combination of reagents will add a chlorine to one carbon and OH to the other. As I think about it, I don't see any really good reason why it wouldn't go the other way with the OH over here and the Cl over here. But it doesn't really matter because after the next step, you'd still get the same epoxide. So the last step in this synthesis shows forming an epoxide from this chlorohydrin, and that requires any strong base. You could use, well, I don't know about hydroxide. I guess hydroxide would work. I would feel safer using a bulkier base, like potassium terbutoxide.
How about sodium hydroxide?
I think that would probably work. I just would be a little worried that you would, well, I don't think you're going to get an SN2 reaction with hydroxide.
Oh, the answer key says, sorry, I'm following with the answer key and it's saying
Yes, I know. I know you always follow along with the answer key. I'm just showing you another correct answer. Really, any strong base would work. Sodium amide and liquid ammonia would work. Any strong base will be fine. Potassium terbutoxide and terbutanol would surely work also. You want something that's going to cause the deprotonation of the OH to make O-, then the O- attacks the carbon that has the halogen on it, and you form the epoxide. So any strong base will do. We know many of them by now. Let's see that. Yeah, it is sodium hydroxide and water. That's fine. The next one starts with an alkyne and changes it to a cis-alkene. We have the same carboxylic acid and the same hexyl group. So we're going from an alkyne to a cis-alkene. That's hydrogenation with Lindlar catalyst. We learned about that in chapter 9. And then we're changing the carboxylic acid to an acid chloride. The reagent that does that is thionyl chloride, SOCl2. And then we're converting the acid chloride to an ethyl ester. You could do that under either alkaline conditions or acidic conditions. You could take sodium ethoxide and add it, or you could add ethanol with an acid catalyst.
we can add sodium NaOET, right?
Yes, either way, either acidic or alkaline conditions would work. And then we're using the same alkene in a Diels-Alder reaction. You can see the ethyl ester group and the hexyl group are cis to each other in the product, just like they are in the starting material. Those two groups are cis to one another. So what we've added, the diene portion, is over here. And that should look familiar to you. Those 5 carbons come from cyclopentadiene. Whoops. That wasn't what I intended at all. That's a little better. So the 5 carbons I've noted in red come from cyclopentadiene. That's a Diels-Alder reaction. Let me just make sure I'm matching. Yup. And again, I don't like using these abbreviations any longer, because as I said, my experience is they confuse students. But I don't have room to draw the group out, so I'll have to leave it as CO2ET. But it means this. It means C double bond O is attached to that carbon, then OET. That's what CO2ET means. It means ethyl ester. And then finally, we're starting with this carboxylic acid, and we're changing from a hydrogen at this carbon to a bromine at this carbon. We just covered that. That would have been in chapter 22. Oh, wait a minute. It's 2 steps. It's bromine. Followed by water. Bromine and phosphorus tribromide followed by water. That replaces one of the alpha hydrogens with a bromine. And then we need to get a nitrogen in there somehow. A nitrogen to do an SN2 reaction on both bromines and close the 5-membered ring. This is proline, by the way, one of the amino acids. And I think excess ammonia would do that. You need an excess because it's an acid and you need a base to deprotonate the acid. So that's how to complete those syntheses. It did use a lot of reactions from other chapters. I admit that. But it's good practice for the final exam. And now some of the more familiar fill in the product type questions. So that first reaction we did in class today. We already know what sodium borohydride does to any ketone or aldehyde. It reduces it to an alcohol. Aldehydes to primary alcohols, ketones to secondary alcohols. So this will just reduce the aldehyde to a primary alcohol. Simple as that. You get a sugar alcohol. We talked about that in class today, and we'll review it on Friday. The next one's kind of tough. That's going to do a Robinson annulation. But that's a reaction you have to know. We covered it in chapter 23. And the way I recognize it is I see an alpha-beta unsaturated ketone that also has a methyl group on the other side that can be deprotonated. So I think the only way to prove to you that we get the product that is listed in the answer key is by doing the mechanism. And indeed, I would not know what the product is without doing the mechanism. We start by treating it with base, sodium ethoxide and ethanol. We get our ethoxide ion. And that's going to pull off the proton. And put the minus charge on oxygen. You get the enolate. So there's your enolate. And in chapter 23, we said that enolates like to add to the beta carbon of an alpha-beta unsaturated ketone or aldehyde. That's the beta carbon. And this is the alpha carbon. So let's copy that molecule. Again, I realize that's not as easily done with a pencil. But the enolate will form a new carbon-carbon bond. And the new bond forms between this carbon, that carbon there, and that carbon. That's where the new bond goes. This is the part where it's very easy to lose a carbon if you're not careful. I've made that mistake many times. Let's see, that's the new bond. So we've got a phenyl group over here. And we, other than that, have 4 carbons. So 1, 2, 3, 4. It's not going to let me do that. I'm sorry, I'm going to have to go with wonky bond angles. It's trying to put the oxygen into the ring. So you get that enolate. Yes, that's right. There's, besides the phenyl group, it's 1, 2, 3, 4 carbons. The third carbon has the O on it. 1, 2, 3, third carbon with the O, and the methyl group. So that's the intermediate that you get. After that, we protonate the enolate. Using ethanol, since that's what we're given. So we need to use that as our proton source. So we reform the carbonyl. The double bond swings out and forms a new CH bond. And we break the hydrogen-oxygen bond. And we get that ketone. And I believe I actually accepted that answer, although I don't think it's the best answer. Yes, that's this compound over here.
What do we do with the H3O plus?
That comes at the very end. What you do with it is you'll get a compound that has an enolate, and the H3O plus protonates the enolate. That's what it's for. It also will cause the dehydration. In the next step, we pull a proton off of this carbon so that we can get a 6-membered ring. Ethoxide is still around. I think I'm going to swing this around a little bit. I just rotated around that carbon-carbon single bond so that we'd have, wait, let me get rid of these lone pairs sitting in space. There we go. So that these 2 carbons would be near each other. and you can see that you'll get a 6-membered ring. 1, 2, 3, 4. No, you don't have to write the numbers to get credit, but it makes it easier to see. And in the next step of the Robinson annulation, we close the ring. So we form a new bond between carbons 1 and 6. So let me see. Carbon 6 is this one. This is carbon 1. This is 2. Three and 4. And then carbon 5 hasn't moved. It's still here. So let's see now. Carbon 4 has the phenyl group on it. Carbon 3 is a CH2. Carbon 2 has the carbonyl. And our new bond is between carbons 1 and 6. And on carbon 6, we still have O minus. Like that. And then I would expect the oxygen would pick up a proton from ethanol. Just like before. And you'd get that aldol addition product. I've forgotten some carbonyls, haven't I? There's still carbonyls on this carbon. There we go. That's better. And next, I would anticipate that we will get dehydration because we'll get an extremely stable tetrasubstituted double bond. So that will still happen with the same base. This could also happen under acidic conditions, but I want to use the mechanism that we used in class because that's what everyone's familiar with. Oops, what am I doing? It is not an E2 reaction. It's an E1CB reaction. And then we lose Hydroxide is a leaving group. And that gets us to the Robinson annulation product. Like that. Oops, I forgot to lose the OH. And put in the double bond. There we go. So I think a dehydration would happen quite readily because you get a tetrasubstituted double bond. And the H3O plus is just to neutralize the base. So that was the answer I was looking for. I guess I also accepted this other one. But I did expect them to recognize that you're going to close a ring between the methyl group and the carbonyl. And it doesn't matter which carbonyl you use, they're the same. So that was the answer I was looking for on that exam. And again, the way you know you're going to get a Robinson annulation is you're going to make an enolate and you're going to treat it with an alpha beta unsaturated ketone that has on the other side of the ketone a methyl group, or at least some other carbon. Doesn't have to be a methyl group, I suppose, but a carbon that you can deprotonate to get an enolate. So that was the answer I was hoping for. Good. Robinson annulation is a pretty lengthy mechanism. But I don't think I would have known what the product was without writing out the mechanism. For the next one, it might also be helpful to write out the mechanism. Oh, wait, I don't want to take it from the answer key. I want to take it from the blank exam. So this one here will start with that same ketone. We'll deprotonate with ethoxide. We'll treat with this aldehyde. It will do an aldol reaction. The way we know that is that the acceptor molecule has no alpha hydrogens, and the acceptor molecule is an aldehyde. That means we're going to get an aldol reaction. And H3O plus acts like heat, though I don't think you need any heat. You're going to dehydrate no matter what because we've got a benzene ring here. And the double bond that you get is conjugated to that benzene ring. So in class, we said that's going to dehydrate no matter what. You couldn't stop it even if you wanted to. So we have our ethoxide ion. This part is much harder on ChemDraw than with a pencil. The ethoxide will deprotonate alpha to both carbonyls. And make the resonance stabilized enolate. This enolate then will attack benzaldehyde and do an aldol reaction. And the next thing that happens in our aldol reaction, that oxygen gets protonated by whatever we're given as a solvent, which is ethanol in this case. Remember, the base is not always NaOET. Don't memorize that. The base could be something else. This would have worked just fine with hydroxide, I think. Or another alkoxide base. So you get this alcohol, this initial aldol adduct, and that's going to be very unstable because when you lose water and get a double bond here, the double bond is conjugated to the benzene ring as well as to both carbonyls. So you couldn't stop this dehydration from happening even if you wanted to. It starts by pulling off that one remaining alpha proton. And we'll do the E1CB elimination. So you get the enolate, and the enolate then completes the E1CB elimination by losing hydroxide as the leaving group. Hydroxide is normally a pretty lackluster leaving group. But in alkaline solution, it's good enough. And you get that compound. So that was the one I accepted for full credit. That included the dehydration. This next one really belongs more in exam 3, where we did reactions at the alpha carbon, but it starts by pulling off one of these alpha protons with the ethoxide. And you get the same enolate And this then does an SN2 reaction on 1-bromobutane. Bu means a butyl group. And you just add a butyl group in between the two carbonyls. One, two, three, four. Again, checking the answer key. Yep. And the next two are an aldol condensation and a Claisen condensation. But I just need to take a quick bathroom break. Oh, there's my cat. You can see them later, Barnaby. I'm walking in the dark and there's a cat. Okay, so the first one we know is an aldol reaction. The way we know that is because we're given two ketone molecules that have alpha hydrogens over here. And these can be pulled off with any suitably strong base. You could even do a directed aldol with LDA. So the ethoxide deprotonates alpha to the carbonyl. What's wrong, Barnaby? Can't wait to say hi to them? As if you'd ever say hi to them in real life. You do not like people, except for me. Which is a shame. So the aldol reaction continues. We reform the carbonyl. The enolate attacks the carbonyl of the other molecule. That's pretty much the definition of an aldol condensation. Is a nucleophilic addition to a carbonyl where the nucleophile happens to be an enolate. Well, that's the new bond we just formed. And so you get this alkoxide intermediate. Then, as you recall, the alkoxide intermediate gets protonated by the solvent. In this particular case, the solvent is ethanol. The solvent might not always be ethanol, but in this case, it's ethanol. And from that, you get the aldol addition product. Which looks like that. And then you'll notice it says heat. That's a signal that we're going to get dehydration. And the dehydration starts by forming the enolate again. Using the same base that we're given. And you get this enolate. And then the enolate collapses to expel hydroxide as the leaving group. The double bond shifts over. And we get the product. So again, the way you recognize that it's an aldol condensation reaction is that you're given a ketone or aldehyde with at least one alpha proton. That way, since it's two of this molecule, both the enolate and the acceptor molecule are ketones. And in class, we said if the acceptor molecule is a ketone or aldehyde, you'll get an aldol reaction. And the aldol proceeds as usual, give the initial addition product, which then, because we heat the mixture, this undergoes dehydration, and you get the dehydrated product. The other question on this page, I'm taking the liberty of erasing quickly because it's going on video. The other reaction on this page is going to be a Claisen condensation reaction. And the way you know that is you're given an ester with at least one alpha proton. So our acceptor molecule is going to be an ester. We will start just like before by deprotonating alpha to the carbonyl. That forms the enolate of the ester. Which looks like this. That enolate then adds into another molecule of the same, since it says 2 of this molecule. So the double bond attacks the carbonyl carbon. We break the carbon-oxygen double bond. Actually, I'll use this molecule. Whoops. So that's the new bond we form. This carbon is attached to O minus. I'll put OH for now and change it to O minus. There's an ethoxy group, and there's CH2 family. And now, because this is a Claisen condensation rather than an aldol condensation, we now have a decent leaving group on that carbon. So we don't protonate the oxygen, but rather we lose the leaving group. And you get a molecule that looks exactly like the product. And so that's the product that you get. Now, if we were actually writing out the mechanism for credit, we would have to show the next deprotonation, because we're still under alkaline conditions. So we have to show this deprotonation. It cannot be prevented as long as we're in alkaline conditions. That proton is particularly acidic because it's between two carbonyls. And that's always going to be the case for a Claisen condensation. Claisen condensations give you beta ketoesters. And so you would get this enolate. And then you add the dilute H3O plus. That dilute H3O plus will protonate the enolate at the carbon atom, not on the oxygen. And will give you the same molecule back. We already knew that 2 steps ago. So to answer this question, we really only needed this structure. But if we were drawing out the full mechanism, it would look like that. So any questions on any of those products? People are dwindling. I realize we've gone well past 8 and we still have to do the mechanisms. How many are there? 4. Good heavens. Well, I'm in it for the long haul. Wait a minute. This is the exact same reaction. Maybe since we are getting late, the number of people are dwindling. We'll just go over the mechanism that's in the answer key. This first one is going to be a Claisen condensation, but it's a crossed Claisen because it's using 2 molecules of 2 different esters. You can tell that the molecule on the bottom is going to be the acceptor molecule because it has no alpha protons. The only one that can be deprotonated is the molecule on the top. So mechanism looks like exactly what we just did. First, we deprotonate alpha to the carbonyl using the base that we're given, which is ethoxide. And then that enolate, this is that same enolate that we get. I just used pH for the phenyl group. That attacks the second carbonyl compound and gives this intermediate. And then remember, in a Claisen condensation, we don't protonate the oxygen because we already have a decent leaving group attached to that carbon. So we reform the carbonyl, kick out the alkoxide as a leaving group, and get this compound. And I'm trying to avoid, wait a minute. Oh, I see, I turned it over for some reason. Let me just draw out the ester group. I have no idea why I did that. So there's that ethyl ester group. The mechanism continues by the base that we're given pulling off the proton that's between the two carbonyls. You could push the minus charge onto either oxygen. It doesn't matter. Not only will we not take off points, we won't even notice. It's just another resonance form of the same molecule. And that gives you this enolate. The enolate gets protonated at carbon by H3O+, which we then add. Remember, we form the product, what actually is going to be our product, in alkaline solution. So the base is going to pull off that acidic proton. It cannot be prevented. So you have to show that as part of the mechanism. That gives you the enolate. And then we add H3O+. That will neutralize the base and put the proton back onto the enolate to give you the product. So this is just a Claisen condensation reaction. The bottom one is a mechanism that we'll get to in class on Friday. This is called formation of a glycoside. And as you can see, the only change in the molecule is going from OH to O-ethyl. And we treat it with acidic ethanol. If instead we treated it with acidic methanol, then it would change it to O-methyl instead of O-ethyl. But this mechanism we actually learned in chapter 19. It starts by protonation of the OH group because we're going to go from a hemiacetal to a full acetal. And we learned about hemiacetals and acetals in chapter 19. So we protonate that OH group using the acid that we're given. That's the protonated ethanol. That gives this intermediate. And then we lose water as a leaving group. The oxygen in the sugar ring can help out, just as it could from any hemiacetal, and forms a double bond in the ring. And then the alcohol, the ethanol, can attack that new carbon-oxygen double bond either from above or below. In this case, we're showing it happening from below because we see the ethoxy group on the bottom pointing down. So that means attack of the ethanol happens from below, like shown here. And then all you need to do is show a solvent molecule, the ethanol, pulling off a proton from that oxygen. That gives us the product. So we'll cover that reaction on Friday. That's a reaction that sugars can undergo, but really it's a reaction we've already learned. It's going from a hemiacetal to a full acetal. We learned about that in chapter 19. Good. The next one looks to be an intramolecular aldol reaction. And the way I know that is we're given a diketone and we form a ring. So tricky part here is knowing where to deprotonate, whether it's at this CH3 or this CH3, since the molecule's not symmetrical. The way we know it's at this CH3 is because when we number the carbons, 2, 3, 4, 5, 6. Then we can see that we form a bond between carbons 1 and 6. This is carbon 1. And this is carbon 6. Carbon 6 has that methyl group on it. So carbon 2 is over here. It's the carbonyl. Carbon 3 has the 2 methyl groups on it. So that's how you know that you pull the proton off on that side. 4 and 5. So we start by forming the enolate on the carbon we've labeled 1. And then that enolate attacks the carbon we've labeled carbon 6. That forms a new bond, this bond right here, between carbons 1 and 6. And then we know we're going to get a dehydration for 2 reasons. First of all, we see that we're given heat. And second of all, we see a double bond in the product, the carbon-carbon double bond. That means we must have lost water. So we start by closing the ring between forming that bond between carbons 1 and 6. On carbon 6, we have O- that came from the carbonyl. Ooh, I just realized something. That's missing an arrow. There should also be an arrow like that, because we break that carbon-oxygen double bond. And that gives us this intermediate. And then in the next step, we protonate the alkoxide using whatever the solvent is that we're given. In this case, it's water. So water puts the proton back on, and then we do the E1CB elimination, which starts by the base that we're given, hydroxide, deprotonating alpha to the carbonyl to give the enolate, and then the enolate completes the E1CB elimination by reforming the carbonyl. The carbon-carbon double bond shifts over one place, and we expel hydroxide as the leaving group. That gives us the product. So the mechanism is just like any other aldol condensation reaction. It just happens to occur within the same molecule. Good, and the last reaction is hydrolysis of an iminium, which is normally part of the storic enamine reaction. The only added twist is that the iminium species happens to be cyclic. So that means that the aldehyde that we get in the amine stay in the same molecule. But the mechanism's identical. The mechanism starts with attack of water. Remember, with H3O+, H2O is always present. So H2O adds to the carbon that's double bonded to the nitrogen, and you get this intermediate. Then water, which is the solvent in this case, pulls off this proton, and you get this neutral species. And then we need to protonate the nitrogen so that we can lose nitrogen as the leaving group. And so you get this intermediate. That then breaks open the 6-membered ring. We form a carbon-oxygen double bond right there. We break the carbon-nitrogen bond, and that's where the NH-ethyl comes from. This nitrogen is this nitrogen. And then we have 1, 2, 3, 4 CH2s in between. 1, 2, 3, 4 CH2s in between. That gives us this intermediate, which is just the protonated aldehyde. So we show water pulling off the proton from the aldehyde carbonyl oxygen, and that gives us the product. It's the same mechanism we learned in class for any other iminium species. It's just that the amine and the carbonyl group happen to be tied together. So instead of getting a separate amine and an aldehyde or a ketone, you get just one molecule. But the mechanism's identical to what we covered in class. And that's pretty much it for this exam. I have some editing to do on this answer key, which I'll try to get done tomorrow. If I can get it done tonight, I'll get it done tonight. Other than that, I can see there's only one other person here besides me. Thank you for sticking it out. And this video will be posted on YouTube probably sometime tomorrow. So I will see you all on Friday, if not before.